Okay, any questions? No one's playing with their phones, right?
Yeah, actually, I looked at chapter 2 and I couldn't find the little end. I found a number that's like really big. I get that, but what is it?
Yeah. I mean, that's something you learn in microelectronics too. We can pull it up real quick. And in chapter 6. Actually, let's see how good the index is. We'll look at emission coefficient in the index and see if it's there. Or little n. I'm just curious in both cases. No, not there. Let's see little n. See intrinsic carrier. Oh, that's Ni. I don't know, that's kind of something you should know from basic microelectronics, but I'm sure I went in there. It's on page 46.
46, you said?
46. And 39. All right. Let's, any questions on the homework? Problem number 2. All right, well, we could talk about projects and two-stage op amps and the consideration, but let's spend time on verifying your answer. All right. Well, let me just make sure, because this would be a good quiz question for today. So let's see. This was 18. Just to make sure we follow how to do this problem, number 2. What's this voltage right here? VD1. What's this voltage right here? VD2. So what's the current flowing? Minus VD1 minus VD2 over R1. So if I asked what is the voltage right here? That current times R1 plus VD2. So everybody's going to understands that, right? For today's quiz. I mean, we've done this over and over. We did it for the beta multiplier. We did it for all kinds of references. So if I give you a problem and you have to go this voltage minus this voltage divided by R is the current, and then the voltage here would be that current times R plus VD2. I don't know how much easier I can make it. All right, so there, verified. What's this reference voltage then? Yeah, it'd be R2 over R1 times VD1 minus VD2, where VD1 is VT natural log of I over IS, and VD2 would be natural log KT over Q times ID divided by KIS. Now I'm doing that all in my head because it makes total sense, but do we need to spend time on this if it's an open book quiz? All right. So let's go back to the topology for the projects. Whoops. And I want to talk about the biasing a little bit more, and then I want to go over the beginning of chapter 24, which covers like things like DC gain, what is power supply rejection ratio, common mode rejection ratio, all those things that are required here for the project. Okay, so one thing that I would stay away from is in order to make the gain, meet the gain requirements, is I would stay away from three-stage designs. Okay, especially if your three stages all have voltage gain, that's going to be a pain. But go ahead and try it, and you can waste some time, and then you'll come back and say, oh, he was right. Okay, so let's go talk about the push-pull output stage, and I'm going to derive some of the different situations here. So refresh my memory. This is where we left off last time. This is the push-pull output, or the output of the op-amp. Why would I use this topology? Simple terms, why would I use it? One reason. Yeah, more output swing. Also, if you look at the other output topologies, like this one right here, where we had, this was the first op-amp we discussed, where we have a bias, and this is V out. What's the amount of current that I can sink for this op-amp? It's limited by this current mirror, correct? So this was a common source stage, and this is limited by the current mirror. So if I ask what's the maximum amount of current that I can sink in my output, it's whatever this current is, say 20 microamps. That's a huge limitation. If I use this topology and this is not a bias voltage, this can go up, this guy can turn on, and it can then pull considerably more current on the output, and it can source more current. Everybody see that? So by not having these as bias voltages, and I can pull this one down and move it up, and I can pull this one up and move it down, I turn these on and off, and I can actively drive or control the output. In other words, I'm not simply relying on a current source. So when you look at the topologies, especially the first ones in chapter 24, you're going to see these. These are not going to be good for your design unless you run with lots of current. Okay, so now here's how I'm going to bias these, and we're going to go through this a little bit today. I'm going to put a transistor here. Now I'm going to show the biasing, and then we'll talk about a little bit more. I'm going to put a transistor which has the following biasing. And just as a sanity check for myself, how do I implement this current source? I can use a cascode. I could use a simple NMOS going to V bias 4. All right, this is equivalent to this. And this is my bias 4. Now I'm going to make this device have a width of W over 2, so its current is I over 2 of the bias on these. We'll talk more about this in a moment. If I do that, what is this voltage here? This is all repeating stuff we've gone over 100 times. What is that voltage? VDD minus VSG times 2. Anybody agree with that? Does that challenge anybody at this point? So what do I have here? There's a VSG. There's a VSG. And I have a current mirror that I'm using. I call this VP CAS if you remember the bias circuits. Any questions about that? So when I give you this on the final exam or on a quiz, nobody's going to mess up the biasing here, right? You're all going to follow what's going on. Now, I'm going to put another transistor here that has, of course, there's no place for current to flow yet here, that has a W over 2. And I'm going to go over here to 2 gate drain connected transistors. I'm going to ask you, what's that voltage? And let's put current source here, I. What is this voltage? Two VGS, and I have a VGS here and a VGS here. Turns out that controlling the current in the output stage is hugely important because it sets your GM2, which if you recall in our compensation scheme, that was the GM of the second stage. Remember when we did this pole splitting? That was the compensation or the GM. And if that's moving all around, when you do the frequency response and you do the compensation, you're going to feel pain. Any questions on this part of the biasing? And what did I call that voltage in my bias circuit? What did I call it? VN CAS. On the side of your back. Keep looking at it. I'm like, it must be interesting. All right, that's called VN CAS.
Is that an NMOS in the middle of that?
This is an NMOS, and this is a PMOS. I'm going to draw it neater on the next page. I just want to give you an idea for the biasing before I go any further. Okay, so I'm going to leave off that biasing for obvious reasons. It clutters up the schematic. And I'm going to sketch the push-pull output like this. And you know what? Just to be crazy, let's use the sizes from the book, the long channel process. Or wait, yeah, let's use the long channel process. What was the typical NMOS and PMOS sizes?
30/2 and 10/2.
Okay, so I'm going to make this a 5/2, and this one 15/2. And then I'm going to go crazy here, and I'm going to make this 300/2. And this one 100/2, and this right here will be my output of my op amp. And now I'm going to pause. I don't know where the currents flowing in each of these are, but what was the bias current in the book in that chapter for those size for long channel? So if I had 20 micro, here I'm going to have 10. Here I'm going to have 10. Again, I haven't drawn how I get that yet. And then what do I have here? What do I have here? What? Oh, it's 20, yeah. 200, thank you. Everybody agree with that? Now, I'm going to finish my schematic. I'm going to come up here, and I'm going to put a 30/2 device.
Why is that 200?
Isn't the table the bias current for a 30/2 and a 10/2 20 microamps?
Oh, yeah.
So 300/2 would be 10 times that, or 300 or 200 microamps. Okay, and then here I'm going to come down here and I'm going to put this as a 10/2. And then I'm going to come back and I'm going to ask you, what is this current? 20. And what is this current? And this is actually called a floating current source, and we're going to talk more about that in a little bit. But before I move on, does everybody understand the biasing? Does it make sense? All right. So now, what's the input of I just told you. What's the input of an op amp? A diff amp. So here's what I'm going to do. I'm going to put my diff amp in by doing the following. I think I want to make sure I teach this right because I want you to be able to do a wide swing input too. All right, we'll just leave it like this for now, and I'm going to come over here, and I'm going to put another device. I'm going to draw it a little, I'm going to, yeah, I'll draw it like this. We're going to modify this later. Then you get to pick what you want to do or you think is going to be the best. So I'm going to do the following. And I'm going to ask you, this is a 30 by 2, before I draw the diff amp, what did I do right here and why? I haven't finished the diff amp, but does everybody see this is equivalent to a, well, these two are equivalent to a 60 by 2. And so now I'm going to finish drawing my inputs. And I'm going to connect this to V bias 4. And I'm going to connect this to V bias 4. And this to VN CAS, VP CAS. And then here are my two op-amp inputs. And this is going to be my first op-amp design. And before I go further, I'm going to put this as ×2, or put two of them in parallel. So this would have a width of either M = 2 or 20 by 2. I prefer, especially nowadays, just to replicate the transistors rather than adjusting the widths, except these. You can put them in series to get 15 by 2. So for example, if you do this, and this is a 10 by 2, and this is a 10 by 2, that's equivalent to a 5 by 2. So if you go get a job and you're working at Qualcomm, for example, they will do everything in like the most edge of the wedge process. It's like 7 nanometers. And so you can't, like in the olden days, change the device width and length. You have very well-defined values you have to use. So you have to design with standard transistors. And then to get different sizes like I've shown here, you have to like put them in parallel or series. So this would be M = 2, where you take 2 transistors and put them in parallel. Okay? Any questions about that? Yes? Oh, here, let me be more precise. Like this. So this would be node 1. This would be node 1, 2, 2, 3, 3. All right. And I might have assigned that at the end of chapter 6 to show that those are equivalent. Of course, it's super easy to show parallel ones are. Okay, so why did I put these two in parallel? Because it's the exact same as this, right? So this with ×2 is the exact same as this. So I could put up here, just to put it, this is a ×2, or an M = 2, or a 60 by 2. So why did I draw it like that? And the answer is biasing. I want to have the 20 microamps to flow down here, but I also need 20 microamps to flow through here, because I have 40 here. And then what's the current flowing in there? 20. Okay, so let's see if we can figure out how this works. Before I do that, are there any questions? I got a question. What is the minimum input common mode voltage and why? Yeah, VGS plus VDS SAT. And what is the maximum input common mode voltage? VDD minus the threshold voltage. Because remember, I only need a VDS SAT across that, so that tells you your input range. Now, if I ask you what is the gain to this node, it's basically the diff amp gain, the GM times R out N in parallel with R out P. R out N in parallel with R out P. What is the gain from here over to here? I'm gonna derive that in a moment. I'm gonna derive the diff amp again, because I bet if I gave a quiz today and I said, show me, closed book, show me what the gain of the diff amp is, 90% of you would get it wrong. Am I wrong? Yes? Maybe I'll change the old quizzy today. Okay, so let's make sure we understand what's going on. If I drive this voltage up, what does it do to this voltage? What does it do to the current in here? Increases. What does it do to this voltage? Decreases, goes down. I mean, you go to a gate, you drive the gate up, the drain's going to go down. It goes down. If it goes down, what does it do to this transistor here? And so it drives the output high. Now, the way this works, you have constant current, and I'm going to prove this in a moment. This node actually goes down as well. So this one turns on, and this one shuts off. So see the pushing and the pulling? I'm not having to supply current to this transistor. I'm supplying all my output current to the output. And if you look, I got 200 microamps plus 20 microamps plus 40 microamps. This op amp minus the bias circuit takes 260 microamps, or roughly a quarter milliamp. You see how easy it is to estimate the power and the current draw? Because I just do each branch, and then I multiply times VDD, and that tells me the power dissipation. Easy, right? So if I'm not meeting specs, I can increase the size of these, burn more current, and I have more drive. So wider, stronger transistors. Questions? It's making sense?
Power equation would
Be this plus this times VDD. Yeah. So now I got a question. Is this the non-inverting or the inverting node?
non-inverting.
That's the plus input of the op amp, and that's the minus input. So let's go the other way, but let's do it from this side. Let's go with this side going up, which we think will make the output go down. So if this side goes up, what happens to the current in this side? Goes up. What happens to the current over here then? What? If I increase this, this pulls more current, this voltage goes down, the VSG increases, I get more current. What does it do to this side? It's a current mirror. It goes up. If the current in this side goes up, what happens to this node? Goes up. Anybody not follow that? Turn this transistor on, I pull more current through this side, I pull more current through here. But this one, when I pull this up, this one shuts off. So that causes this node to go up, which causes this node to go up, which then in turn does what? Turns this off and turns this on. And now I can get these where they operate within a VDS SAT of the power supply. For your design, if you went with 50 millivolts, you'd be able to operate linearly within 50 millivolts of your power supply. Any questions?
So if the top one's off and the bottom one's on, it's still drawing 200 microns?
No, when you're transitioning that, when these start to move apart in a real op amp, that's when you're driving the output to some value. And through negative feedback, it drives these back to be essentially the same value. So if you're driving a capacitive load and you've charged or discharged the capacitance, and when you're done, these go back to the same value. Once they go back to the same value, all the currents go to the same. But what happens if you put a resistive load here? The gain's going to go down, but also I got to supply the current from this one. So what you might do in your design, hint, hint, is size this up so it supplies more current and you get what is called an offset. In other words, these have to be a little bit off in order to make this current equal this current, because you size this one up because it's got to drive a resistive load. An offset hopefully is only, if you have high enough gain, is only a millivolt or something. All right, there's trade-offs in real op amps. Now, I'm going to go through this part of the circuit in a couple steps. However, I want you to notice how I'm assuming these go up together. What you can do in real life is you can put a capacitance in between those two, and this acts like a battery, acts to keep the currents going. And so if this side goes up or down, it feeds and helps the other side go up or down in easier fashion. And so you don't have to spend extra charge charging and discharging the input capacitance here. We're going to put the compensation capacitor in. So this is a low power trick that I've seen used in industry where they will put a capacitor across there to make these move better to keep the power down. For example, in like a hearing aid. This would be a common circuit you would use in a hearing aid where you would have the speaker you're driving and you want your batteries to last forever. And if you know anybody that has hearing aids, batteries don't last long enough. Okay, so it's a big deal. All right, any questions before I go through each of these circuits? Now, notice down the road, not today, but down the road, we could put a PMOS diff amp here and put them in parallel, have them both on, one off, one on, the other off, the other on, so that we have input common mode range, and it also extends basically rail to rail. Okay, of course, we're always limited by our output, but right now we have a significant loss because we have to keep the input above a certain value. I didn't give you that I recall, a spec on common mode input range, but you may want a design that operates with a really wide input common mode range and a really wide output common mode range. And so you want to change the biasing, you want to change the circuitry so you have a PMOS diff amp. Okay? And you have to be able to accommodate that because one issue we have here, if this goes too low, what happens to these transistors here and why? If I drive these down, what happens? They turn off. If I drive these down, I don't have enough voltage across here. These all shut off. They shut off. How much current's flowing in there? Zero. How much current's flowing in there? Zero. How much current's flowing in there? Zero. So this whole stage is off and it doesn't work. So we're going to talk about that problem later. But you see how important the biasing is here? Okay, so I'm going to focus on this part. Now this is a two-stage op amp. I got a gain of the diff amp and I got a gain of the output stage. Okay? So here's my output stage. I'm going to do this in a couple steps just to make sure it's clear. So I'm going to have the following. Actually, before I do that, let's do this, which everybody in lab should be able to derive. What is V out over V in? Oh, I gotta explain it. I can see my future of coming up here and just telling you answers and then getting yelling at you when you don't know it. But for now, I still have to explain things and teach. That's not as funny to you as it is to me. All right, what's the VGS here? Correct, V in. What's this AC voltage? 0. So what's the VSG here? 0 minus V in or minus V in. So what is this current here in terms of V in? And what is this current here in terms of V in?
Negative GM.
So far, so good? And now what's the total resistance here only due to the output resistance of each transistor? And then let's see, this current comes in like that. That one also, if we put it, it comes out in the same direction. If I put V in, so I can write this as V out equals minus GMN times V, let me start over. Minus GMN plus GMP times VN. Does everybody agree with that? Oops, times R out in and parallel to R out P. So I'm pulling it negative backwards, so I get my negative sign. Then I've got my GMN times VN plus my GMP times VN in the same direction, and it's minus because I'm pulling the current backwards. So if I draw, just as a sanity check, as I draw this current going in the opposite direction, everybody would agree it's GMP times VN, right? It's being pulled out just like GMN times VN is being pulled out. Do we agree? And so V out over V in is equal to,
So shouldn't that, should be negative G? Shouldn't the negative sign go inside, not outside?
so isn't this voltage, if I use this one, if I use GMP times minus V in, isn't this minus GMP times V in times R out P in parallel R out in, minus GMP times V in times R out P? If I pull it backwards, isn't it minus, because it's flowing backwards, minus GMN V in R out P in parallel with R out in? Who agrees? No? Yes? I'm not seeing any issues. What? You look at it later. Wait, let's make sure you get it now. R, I. What's this voltage?
Negative ion.
Being pulled this way, GMN times VN, it's being pulled backwards, minus times R, minus GMN VN times R. Okay, what if I do this? This current's minus I and R. What is that voltage? And I have GMP minus VN going in, and it's minus GMP VN times R out in. I don't want you to say I'm ripping you off of your education there.
So is it not GMN plus?
No, yes, sorry. All right, so that's my gain there. Now, what I want to do is I want to go back and I want to look at this part of the circuit, and to do that, I'm going to use just a current source here, and that's a source, and that's a source, and so I'm going to do it, my derivation, assuming that there's a current source there, current sink there. All right, so let's do that. And if I do that, what I get is the following. And let's call this and I'm going to leave, I'll draw it, even though we won't use it for now. Why did I draw these having the gates?
Because we're using AC, so they're affecting AC.
Yeah, but what are they in the circuit? Bias voltages. All right, everybody's cool with that? And I write this as the drain, source, source, drain, and I got a source connected to this node, and I got a source connected to this node. Everybody's okay with that? So now what I'm going to do is I'm going to get my nice little red here. All right, and I'm going to say here is VSG. And what is VSG for AC here? VN. All right, so what's the current that flows here? Would everybody agree with that? But hey, I got a current source here and a current source here, so that means this current has to flow up like that. So it has to be equal to, and we'll call this, how about we call it VS? That has to be equal to GMN over 2 times V 0 minus Vs. And that would be if the current's flowing down. So this is 0, so VGS here is 0 minus Vs. 0 minus Vs GM over 2. Correct? Anybody follow? So that means if I increase the current here by 1 microamp, the current in here decreases by 1 microamp. Because when I pull this node up, what does it do to the VGS here?
It makes it smaller, so it.
Makes it smaller, shuts the current off. So I can think of it as the current effectively shutting off or flowing up. Who understands this? Nobody. All right, I'll do it again, but let me finish. Yeah, so this would be for the current flowing down. This current would be GM over 2 times 0 minus Vs, where this is VGS. And then that means Vs is equal to, correct? If I get it right, assuming, I've got a minus sign here. Assuming GMP over 2 equals GMN over 2. I'll do it again because I think this is confusing. But the key takeaway here, and this is a good assumption because the way I've sized these, that this is also equal to V in. So when I get a V in here, I get a V in here. So when I said earlier this goes up the same amount, it's correct. Let's do it again. Any questions before I change?
So, that's the source of the volume?
Yeah. Let me call it, how about I call it VC on the next one? I don't know, I just picked a random letter. How about I call it VDS? All right. All right. So I'm going to call this once again VN. This is AC ground because it's a bias voltage. This is VN. And the current that flows there is GMP over 2 times VN. Why is it over 2? Well, remember when I size this, I have the size. So it halves the GM. All right, that goes over here to a current. How much AC current flows in this? How much AC current flows in this?
0.
So then I come over here and I write, and then we put here V sub ds. All right, and then I ask, what is this voltage?
Yes.
And what's this current then? Yeah, that's not a good thing. That says drain to source, but we know that's not what it means. All right? So, what does that mean? If I flip it around, that means there's a current here, which is GMN over 2 times VDS. And the only way that can be if these are equal, GMP equals GMN, is if VDS equals VN. So if this goes up, this goes up. This goes down, this goes down. And does everybody follow that now?
So they're basically the same voltage.
AC voltage. Oh, because we have the DC biasing. And what did I say was the trick people used to make sure they were the same? Put a capacitance across there. That makes it so that you don't have charging and discharging of things because the signal flies right through the capacitor. So you don't have to worry about the delay. Any questions on that? All right, a couple more derivations here. This I'm going to call V sub M for the minus or inverting input of the op amp. Here I'm going to call this, what a surprise, V sub P for the positive or non-inverting terminal of the op amp. And then I'm going to write that this is VGS1, this is VGS2. And then, because you'll get this on a quiz or a final exam or something, tell me what to do. And I'm learning, so why don't I draw these out? Looking good? So now what?
The running man.
Get the running man out. You think if I stopped videotaping stopped giving quizzes, people would still continue coming to class in circuits?
No, not in circuits, but in this class, yeah.
I think in this class you guys would. I don't think circuits would. All right. So what do I call this voltage source?
The end. Oh, V minus.
So how about I write VM
VGS2 minus VT.
Anybody not follow? The reason I'm going through this in slow, painful detail is because you need to be able to show this when you're doing your problems. It's not like, oh, I know what that is. You need to be able to, I mean, students don't like it when you just tell them the answer. They want to know what's going on. All right. Tell me how to proceed. What's the next thing I have to realize?
VGS1 and VGS2 should be equal.
Well, ID1, ID2.
They're equals and opposite.
So, when I used to teach microelectronics a lot, because there's 2 semesters, I'd always make these unbalanced. Then I give a take-home test and then an in-class test. I especially love to do that over spring break. Oh yeah, the students did not like me.
But they learn.
Yeah, they learned. All right, so then I'm going to write VP minus VM equals. See if I can skip a step here.
Oh, negative IC over GM. 1.
So I'm going to write, going down here, so if I move the VP, I get minus VGS1, VGS2. So I'm going to write this as minus, just to be different, ID1 over GM plus ID2 over GM. And let's stick with the M's here. Anybody agree with that? Now, this is a little bit different because what's going to be the gain with VP and VM here of our op amp? I mean, is it going to be positive or negative? Negative, because what's the gain of our push-pull output stage? It's negative, right? And I define this as my positive, so I have a negative gain times a negative gain, which gives me a positive gain. So it's a little different than what I'm used to. So I get VP minus VM times GMN equals, let's write it like, see if I'm skipping too many steps here, equals minus ID1. Anybody agree with that? Did I skip too many steps? I did? All right, okay, so let's go back here. Variable in the back. Oh, too many. All right, so that would be VP minus VM times GMN, which is equal to minus ID1 minus ID1. Looking good. And that's equal to minus 2 ID1, or minus ID1 equals GMN over 2. Who agrees with that? All right, so now I'm going to go back and focus on this part of the circuit. Here's my ID2, which is equal to what is it equal to? If I put ID2 there. It's GM over 2 times VP minus VM. Does anybody agree with that? All right, and then coming up here from the current mirror action, the current that flows down there is minus GM over 2 times VP minus VM, and that means the current flowing down there is minus GMN over 2 times VP minus VM, and that's flowing into a resistance of R out N in parallel with R out P. This is V out diff amp. Why is it GMN and GMN here through the PMOS? Because the current's coming from the diff pair, and then it's going through the PMOS current mirror. One of my almost asked today in the quiz, I had the reference, and I'm like, I'm going to ask them why in the top of the reference the VGSs don't come into play in the temperature behavior and the calculation of the current or reference voltage. Because it's a current mirror and they subtract out. Whatever current here is the same as there. So if the temperature changes and the threshold voltage changes, or process change, threshold voltage changes, it's mirrored and it subtracts out. That's why current mirror's good. All right, so then finally, what is V out diff over VP minus VM? So this would be positive GM over 2 times VP minus VM, but they're both flowing backwards through here. And it's GM over 2, GM over 2. I add them together, I get GMN times R out N in parallel with R out P. This current of GM over 2 VP minus VM plus this current of GM over 2 VP minus over M. To get rid of the 2, we add together to this. Who agrees?
So those are, so the top current is coming from the current.
Yeah.
And the bottom current is coming from the.
Yep. Oh, whoops, and I did a boo-boo, obviously. Yeah. All right. So let's throw some numbers in. Actually, why don't I throw some numbers in of a real circuit using the long channel, and you tell me, actually we can do it with what we started with. And let me ask you this. In this circuit, what was the gain of the diff amp to this node? Yeah. Well, it's GM times R out N in parallel with R out P, which was roughly what? 333? And then here I made the GMs bigger. What does it do to the gain though? If I make the GMs bigger, what does it do to this gain? Okay, so if I increase the width, everybody would agree the GM goes up. You can see that from the basic equation, right? What does it do to the output resistance and why?
I'll make it go down.
It's gonna make it go down. So what happens to the gain?
Should go down.
Should stay the same. GM goes up, R out goes down. Let's make sure we understand that. So that would be 333 times 333. All right, so let's look at some numbers for that. Let's write the equation for GM in terms of the overdrive voltage. What is it?
KP W over L times V over L.
Oops. Anybody agree with that? What's another way of writing this equation?
Oh, VGS. Yeah.
What's another way?
VGS minus VE.
Everybody's okay with that? So now, if I take and I increase the W by a factor of K, what does GM do? Goes up by K. So now, let's look at the MOSFET. Let's assume I have a MOSFET, and the resistance of the MOSFET here is R out N, which is 1 over lambda times ID. And I keep the bias voltages the same, but I make them really wide so that now I have a K times W width. What does that do to the current?
Goes up. Current goes up. So resistance gonna go down.
And so R out N will go down by a factor of K. So GMN times R out is constant. So now, going back, any questions about that? Let's go back to the push-pull. So my push-pull here, and I used 100 for the K, or M, whatever you want to call it. That's 3,000. I only used 10. What do I expect this R out N to go to? So what will it go to?
5.5.
And then what will happen to this one? So the output resistance will go to, everybody follow? Now, if you have to drive a 1K load, is that going to be enough of an increase in the W? Let's find out. So if I have this resistor of 222K, and I shunt it with a 1K resistor, that's approximately 1K. And the gain of the output, these GMs now would go to 1.5 milliamps per volt, or 10 times 150 micro. Everybody follow that? So now I could write, same thing here, GMN equals 1.5 milliamps. I can write the gain of this stage as roughly AV2 of this stage is equal to 1.5 milliamps plus 1.5 milliamps times 1K, which goes to what? So now my first stage gain was How about this? All right, if my first stage gain was 200, now my gain's gone down to 600. That's our load. Isn't your spec in your projects to drive 1K? Okay, but we're going to talk about that a little bit more. Does everybody see? So you might decide I need to beef up the output stage a little more.
Yeah, you want it matched, right? For maximum power transfer?
Well, I don't care about maximum power transfer here. What I care about is my op amp not dissipating any power. Then all the power goes from the power supply to the load. Okay, any questions about this? I'm covering lots of good stuff. Okay, so let's go back now, and I want to ask you a DC biasing question about this. If I look at the following, if I have my op amp and I do the following. And what's this topology called? It's called a voltage follower, right? Who agrees with that? All right. So now if I ask you, all right, well, what should the output voltage be? 2.5 volts. Right? How much current flows then in the 1K?
Whatever that is. 0.5 milli.
2.5 milliamps. But wait, let me go back here. Without the loads, I had, what was it, 200 micro? Everybody follow that? Now I've connected up a 1K resistor, and now this has to go to, in steady state, roughly 2.7 milliamps. I got the 1 milliamp, 0.2 going here, and then I got the 2.5 milliamps going there. So what I might want to do is, and you'll have to look at, if you size it up only by 10, that may not be enough to supply this. And so this voltage has to go way down. And then that means that your gain's going to drop. So I'm going to do one last thing before we do our quiz. Before I do, any questions on that? That's 0.2 there and 2.5 there.
20 microamps times 8.
Oh, is that more or is that?
Where? This is 200 micro.
Oh, that, it looked like a 0.2. So in that case, if you want to keep up,
Yeah, you just use a wider device. So instead of using 300 by 2, you might try 600 by 2. And the problem with that is you'll get a small offset here in between the two terminals that is used, and we'll cover this more next time, to make sure when there's no load that the current in the PMOS side equals the current in the NMOS, because the only way that can happen is if you start to shut this one off, because it's beefy. Okay? So now I want to do one last thing here. I want you to calculate if the gain of this op amp is, it drops to say 1,000. I want you to calculate all the voltages in this circuit. So the DC gain, we're sitting there. I want to know what exactly the output is. Okay, what is this equal to exactly? Sound reasonable? So this is only DC. So we'll go back here. And I've got my op amp, which consists of two gain stages. I have the non-inverting input tied to 2.5 volts. I have the non-inverting input as my V out. The DC gain here is 1,000, and I want you to calculate V out. Tell me what to do.
Let's get the difference, 2.5 minus V out times A.
Okay, so I get V out equals
2.5 minus V minus
which is,
V out. And then mix again.
and so when I do this, what I get is the following. I get V out is equal to 2,500 minus 1,000 V out, or V out equals 2,500 over 1,001, and that's equal to 2.499 volts, something like that. Does everybody see that? What happens if the gain drops even more? Say it's 500. Their difference is going to be, but you know, for analyzing circuits, you can treat it like an ideal op amp where these two are the same voltage. Right? That makes sense? I guess the key takeaway is they're not. In real op amps, they're not the same voltage. Now, again, when we come back next time, I'm going to show you that when I beef up the output transistor, I'm going to get an offset here to make things work out. That's unrelated to this, but it's related to making sure the biasing is okay. All right, any questions before we do our grade booster? Bring it on! All right.